So, welcome everybody to our third seminar. And I will post the URL of the seminar and we are going to post the videos and the slides there. So, today we have Martin Reinhardt. And I don't have to introduce him, he's already a legend. If you want to find anything about him, go Google his name or ask ChatGPT, they will tell everything about him. But I want to talk a little bit about how we got here. So about a year ago, Martin started downsizing his group. He started graduating his student, never taking any new students. So at least I thought that okay, his research career is over. He's like now moving into research sunset. And then he announced that he's going to go on Singapore, and also started to graduate his last couple of students. So I'm like, okay, he's definitely just going into becoming a beach bum and surf, which was actually true because the first couple of months I called him, he was answering from some remote beach with a very bad phone line, and it was very clear that he was just doing nothing but surfing in Singapore. But then something changed, and all our phone calls became very boring because the only thing he wanted to talk about was Claude. And this his new love of life basically consumed him. And I have known Martin when both of us were graduate students in Monica Lamb's group from like early 90s, and I don't think he has been ever more productive in his life than last couple of months. So let's give the floor to Martin and let's figure out what he has been doing. Martin, go for it.
Boy, I'm tempted not to say thank you for that introduction. And and I just want to say it's not accurate because the surf camps that you were calling me at had very good internet connection and great reception. Okay. All right. So what to talk about? It is, no, now I got to do this. Okay. Coding agents, produce a lot of code. Don't want to review it. So what you want to do is minimize the code that can affect your system correctness. What I'm going to talk about today is this verified compiler that was built by a coding agent I supervised. Combines four validation techniques: testing, which is, we all use testing; credible compilation. The basic idea here is this is a form of checked computation where you do a fairly complicated computation, produces a certificate that it was executed correctly, and then checked. And then formal verification, where you prove that the code actually did what it's supposed to do, satisfies the spec. And then code audits. Most of these were automated. They were done by Claude, not by me. The goal here is to maximize your development velocity while minimizing all of the unverified and unchecked code. Okay, so who's this talk for? First, people who build verified compilers. I'm guessing that's not a lot of you in the audience. Also, anyone who wants to know what it was like using a coding agent for this particular project. I'll talk about what worked for me, what didn't, how I approach it, and how everything worked. And I wrote two papers about this. One's even been accepted at a workshop already, and they're available in archives, so you can take a look at them and see that what I did here. They'll have a more thorough treatment of what I'm going to talk about today. All right, how'd this come about? Well, as Saman mentioned, I was on sabbatical at the National University of Singapore. I had conversations with a lot of people there, including Ilya Sergey and George Pirleya. George is Ilya's student. Ilya's a professor there. And Ilya wrote a blog post on this move, borrow, checker built using the coding agent. Sounded really interesting. So I thought I'd give it a go. So I got set up with VS Code, Claude Code, Lean 4, and now I was all ready to go. And I just needed a project. So what I did was I went back to a project that I'd started in 1999, actually finished in 1999 as well, so-called credible compilation. The idea here is that compilers back then and even today, you just trust them. You give it your program, they compile it, and you run the program, and you trust the compiler. So the idea in this credible compilation paper, which I talked about in a technical report, we had a publication on it, and it was Darko Marinov's master's thesis, was the compiler doesn't just compile the program. It also emits a proof, and you've got this proof checker that decides whether to accept it or not. And the trust shifts from the compiler, which can be this large, evolving, unverified thing, to the checker, which is small, fixed, and verified. The motivation, I said in the paper, was you had untrusted optimizations, so you can get optimizations from anybody or anything. You don't have to worry about what's in them. You can also have mostly correct optimizations. Because you've got the safety belt of the proof checker, you can very aggressively engineer the optimizations, and they don't have to be right to use them. Okay, so for a variety of reasons, we didn't pursue this much beyond 2000. I'd always kind of regretted it. Now I get another chance, another swing at the apple. So I got this stuff and I started. And here's the timeline. In 34 days, bingo, I had a compiler. Okay, relatively small language. And what I want to get out of this slide are a couple of things. And first is it's a relatively non-standard development. So instead of starting with a target and developing it, I started with the smallest thing I could, which is this very simple integer-only language. And then on the blue dots here, you can see that I am gradually adding features to it. And as I'm adding features to it, I'm taking the original certificate checker and the soundness that I put in at the beginning and having those chase my language developments as I go. In the meantime, I'm adding optimizations up here and top in yellow, and I'm proving theorems down here in green. I've got, around day 7, I decided to put a parser in and a pretty printer in, and day pretty printer in as well. I had some theorems along the way. The final top line theorems weren't done until day 34. Now, you'll see Livermore added and last incorrect Livermore run. So what Livermore is, every compiler project needs a set of benchmarks. These are the Livermore loops benchmarks. I think Fortran benchmarks from the 70s and 80s. This language was inspired by Fortran. I added them around day 18, and the last incorrect run was on day 28. Now, everybody's probably thinking, wait, I thought this was a verified compiler. Why do I have any incorrect runs? And the answer is that the verification takes a lot longer than the compiler implementation. So the majority of the time, this project is running unverified as the verification chases the implementation. All right, let's talk about the final lines of code. Specification is 700 lines of code, and I'll get into what that is in the next slide. 3,600 are verified, 1,800 are checked. I got about 1,200 lines of code verified. Those are basically the text interfaces, the parser and the pretty printer. And the proofs are by far the majority of the code. Here I've got 31,600 lines of proofs. All right, and here's what the final compiler structure looks like. Let me go through this. Text program is what we all know as a program. It's written in text and it's parsed. It's parsed into something called an abstract syntax tree. This is basically it's a representation of the program as close to the text program as you can get in lean data structures. Remember that I'm implementing this project in lean. So it's representation of lean data structures, and it has an operational semantics. The operational semantics is basically, it says what the program means. So think of it as a small interpreter written in mathematics, implemented in lean. Okay, so now I know, so now I've got my high-level program, I know what it means. Now I've got to compile it. Now I'm going to compile it using a flattening stage, which goes in and reduces it into a lower level, so-called 3-address code intermediate representation. What you should know about this is basically just the intermediate representation that the compiler uses when it applies optimizations. Then, when I've done enough optimizations, I do a code gen and generate the assembly language program. And again, this is the assembly language program represented internally as lean data structures. And I've got a pretty printer that generates the text assembly, then I assemble it, then I go off. Okay, so see the thing here? This is the assembly language operational semantics. This is basically a machine model of the machine that I'm compiling to, which is the ARM. Now, there's a very important aspect of this, and that is I do not attempt to model the complete ARM semantics, which is a big project. I instead instructed the coding agent, okay, I need a machine model. Build the machine model, but only for the instructions that the compiler can emit. So it goes off, figures out which instructions the compiler can emit, and generates a machine model only for that. So the machine model is this small instead of this big, and it's much more tractable. Let's talk a little bit about optimizations. So optimizations start in 3-address code. You pump them off to this optimization pass, which is not verified, but it's checked. What it does is it emits a transformed program and then runs it through this certificate checker. And the certificate checker sees if the semantics of the transformed program match the semantics of the original program. And so it accepts the transformation, otherwise it discards it. So you go around and around and around this circle, optimizing the program. The way compilers are built is you got all these different optimization passes and you apply them one at a time, and the program gets more and more and more efficient. And finally, when you're done, then you pass it through code gen. Let's look at what's verified. All the green boxes are what's verified. So the guarantee you get is that if I start with a high-level program implemented in the abstract syntax tree, and I run it around as many compiler classes as I want, because the certificate checker is verified, the flattening is verified, the code gen is verified, I'm guaranteed to get something out the back that preserves the semantics of that correctly implements the semantics of the original program. Now, what do I have to look at? I got to be sure that the operational semantics here are correct and they're actually what I want the program to mean. I've got to be sure that the assembly language semantics are what I think the machine actually does. I don't have to look at anything between the gray boxes here. And I also probably have to look at the parser and the pretty printer if I care a lot about them, but I kind of don't. At least in this project. In a real project, of course, you'd have to audit them pretty rigorously. One interesting thing, though, is that if you believe we're working in a world where the coding agent is going to be writing most of your code for you, it apparently is perfectly capable of dealing directly with the lean data structures and writing programs in that language. So in that case, you don't really have to have a parser or a text program, and that part of it goes away. All right.
Martin, can I
So
just ask you something?
yeah,
It's Daniel. I'm surprised at the red and the yellow bits. In particular, I would have expected that the optimization pass wouldn't need to be checked at all, and that ch at least checking the parser and the pretty printer would be much more important because if those aren't checked, it basically means you don't have any end-to-end guarantees at all.
yeah, that's the reason the optimization passes are checked is because they can do all kinds of crazy things and they're more difficult code to write. The pretty printer is just very straightforward. All it does is it dumps out the assembly language as it's represented. The parser can be more involved, but I've been looking at the capabilities of these language models for probably 3 or 4 years now, just because I've been teaching the compiler class. And the parser is the very first thing to come online. They're very well documented. They know how to build them. And they're relatively easy to look at.
But
So
just say a little bit more. Why is the optimization pass a problem? What could go wrong if it was disastrously wrong? I thought the argument is that with the certificate checker, it doesn't matter if it goes wrong.
oh no, well that's the reason they're checked. You were asking me why do you check the optimizations at all? With a certificate checker, it can't go wrong.
No, no, I'm asking why that optimization pass thing is yellow. Why do you even bother to check that?
Oh, because it might be wrong. You're not gonna ship your program off to some random optimization and have it go off and trash your program and say good enough for me. In fact, there were bugs. Yeah,
I'm sorry,
imagine you do register. Imagine you do register allocation, which you can easily imagine. I mean, all of the people who take the compiler engineering class at MIT get the register allocation wrong one time or another.
I think
And
the
while you're
question
doing
I
such
think
big-
is it redundant to both check the optimization pass and also generate the checking and do the checker? Am I right, Daniel? We are
Yeah,
thinking that.
exactly.
Yeah, there is redundancy, and it's on purpose.
Okay.
It's much easier in general to write the checker than it is to write the optimization pass for complicated optimizations.
I guess this seems to contradict what you said at the beginning when you said that the whole point of credible compilation was that it doesn't matter if it screws up an optimization. So that should suggest to me that
Daniel, the reason, okay, it doesn't matter if it screws up the optimization if it's checked. If it's not checked, it matters.
Yeah. Martin, is your meaning of it's being checked is that the certificate checker is there?
Yes,
Oh, okay.
that's what I mean. The optimization runs, it generates a certificate. The certificate checker checks the certificate. If the certificate doesn't establish the correctness of the certificate of the optimization pass, you discard the transform program and use the other one. Use the original program.
So I don't want to drag this on much longer, but just to check that I fully understand, if we took that yellow oval, the optimization pass oval, and we colored it red instead of yellow, so it was unverified rather than checked, it would have no effect on the end-to-end correctness of the compiler.
As long as the certificate checker was in place.
Right.
Yes.
Okay.
Yes. Okay. Good.
All
Let's
right.
go on.
Correctness and performance. Okay, so the operational semantics is about 700 lines of code. Yeah, so all this stuff So performance is evaluated empirically. Here is the performance. What you should take away from the standard slide that everybody shows when they're doing benchmarks, the K01 through K24 here on the x-axis are the Livermore kernels. The Axon optimized, okay, Axon unoptimized has pretty bad performance. You can see this is a log scale. Axon optimized is faster than G4tran-00, but G4tran-02 is faster than Axon optimized. The geometric mean is 2.2 times slower. I'm pretty happy with this result for basically what is a month-long engineering effort starting from scratch. The compile times are a lot longer. And there's a variety of reasons for that, including the fact that they're implemented in Lean. The data structures, I didn't try to optimize I didn't try to improve the optimization performance above what it would be required to make the project sane for me to work with. So I wasn't waiting for compiles all the time. All right, here's the optimization sequence, and I'd like to use this to give you some idea of what this coding agent is capable of when deployed on this problem. So here's a big pile of compiler optimizations. Now, the way these compiler optimizations work is you apply them one at a time, and you keep on running around and around and around and optimizing the program. It gets more and more and more optimized. Now, there's also the question here is, what's the right optimization sequence? Because that matters. So here, I applied the basic principle of how I use coding agents, which is anytime I have a question, I ask the coding agent first. And I told the coding agent, hey, go off and take a look at the generated assembly language from the Fortran program and the Axon program and see what's going on and pick a sequence. And this is what it came up with. Okay. And not only did it come up with this, but as you'll see later on, it wrote all the optimizations itself, wrote all the generation, it wrote everything here. To this day, I haven't seen the code for any of these optimizations. Okay. So, and not only did it choose this, it was happy to give me the rationale. So it says, do the front load for this reason. Do code, loop invariant, constant hoisting, do it one time per run, do estimated fusion, and all this stuff in this order. One interesting thing here is that it thought about putting copy propagation, which is a standard compiler optimization in the suffix, but it said, hey, it's fighting your register allocator. Don't do it. And it went off. And to back this reasoning, it went off autonomously, put it in, ran the compiler with it, ran it without it, said it harms performance, doesn't help it. So I'm going to leave it out. And I'm just sitting here on the side watching this whole thing happen. All right, here are the top level theorems. I think we can skip this. Okay, what did the coding agent do? Well, it designed the source language, specified the operational semantics, designed all the other languages and machine models and their operational semantics. It built all the compiler components. It built the certificate checker. It did the optimization packers. It did all certificate generators, did all the proofs, all of them. So that's kind of what you get out of the compiler at the end. But what I really appreciated about this was how it automates all of the project activities. So it generated all the test programs, including the Fortran to Axon translation of the Livermore benchmarks. Because the coding agent designing the language, it's a language that isn't Fortran. But I like to run all these Fortran benchmarks. Normally, this is a big problem in compiler projects because somebody's got to do the translation. Not with this thing. With the Claude, it gives you the Fortran to Axon translation immediately, removes this big source of friction. I think this is great because if you want to do a programming language project immediately, your benchmarks are much easier to get. It did all the performance and code quality structure audits. Occasionally, I say, it turns out that copying code and then modifying it is a very powerful code reuse mechanism, but it generates code clones. Periodically, I can go off and say, hey, look for any code clones, remove them. Sure enough, it'll refactor the code for you. It's great at debugging. It'll do root cause analysis. It'll do probes for figuring out where the performance problems are. It'll try to change your program, move it back and forth to isolate the bug. And it'll even do the bug fix for you. I didn't do any of the bug fixes. Okay. Also, project management and infrastructure. It does Git coordination. Don't have to use Git. I just say push or pull or whatever the heck is going on in the chat line, and it's good enough. Builds all the test harnesses. I really appreciate the software installation thing. I'm sure everybody here has had the problem where they're using package A version 2.734 and it's incompatible with some other package you're using. So you got to figure out which one's right. Here, it just grinds through that, installs all the software, and it just works. All right. So sounds like it did the whole project, doesn't it? And the question is, well, what did you do, right? What did I do? Well, I supervised, which is something I'm very used to doing, okay? And here's what I did. I supervised the workflow. So I figured out what the next step ought to be, maybe a language feature, maybe an optimization, maybe a theorem. I asked the agent, go off and draft a plan. So then you run probes, these small experiments that resolve uncertainty in the plan. Claude loves probes. You do the probes, and it drafts all this uncertainty. You revise the plan with what the probe shows, and then you execute it item by item once in its own session, ending the validation step. And a key aspect here is meta prompting. You don't want to write the prompts yourself. You want to have a discussion with the agent about what should happen. And when you think you're, harmoniously in tune enough with the agent, you then say, okay, go off and draft the plan for me. And it'll come up with this big detailed plan and execute it. Okay. For this project, finding lean proofs is essentially the entire wall clock budget. I'm sitting here the whole time looking for lean proofs, generating code, generating tests, generating language designs, implementing all of the optimizations, negligible by comparison. Okay. How does the agent fail? So the agent will occasionally lock onto a specific goal and spin. Okay, sometimes the goal is not provable because you're asking it to prove a theorem that's not true. You can often fix this by widening the scope. You go in, you want to pull the agent out of this rabbit hole. So many of you who are PhD advisors, I'm sure, have had this experience with a student where the student locks onto a goal, and your job as an advisor is to pull that student out of the rabbit hole, get them to take a bigger perspective, and do something, more defensible. Sometimes it has overly aggressive pacing. As part of this project, I was asking the agent to apply these very large cascading edits across the entire code base because I'm adding a feature and it touches a whole bunch of stuff. Sometimes you got to do some detailed stuff to make it go through. And if it's trying to do that detailed stuff across the whole code base, it doesn't work. It over batches, gets lost in complexity. So you got to ask it, hey, go back and take more deliberate steps. And when the agent gets under pressure, it starts to whine, okay? It'll weaken the theorem. It'll add an extra hypothesis. It'll leave a sorry. A sorry is an unproven branch of a proof, and it gives you a rationale. And it's always coming back to you with excuses. Hey, this theorem's probably good enough. What's the real goal after all? Or, I'll add an extra hypothesis. And you got to go in and decide if you want that. I was not willing to accept any sorries because if I leave a sorry, there's a hole in the proof and all this code that I'm not looking at may be busted. So I can't have any of these. All right, let me tell you a little bit give you a taste of what it's like to do this. So here's what you're looking at. You're looking at a session summarized. The green is me typing into Claude. The blue is Claude's summary of what's going on because Claude itself generates a whole bunch of stuff and it's too much to fit on the slide. So here I am saying is the three address code is the intermediate representation to the assembly language verified yet. Claude's saying, sorry, got 9 sorries remain. I don't like this because this sounds like a lot of them and it's not good. Then it says, moreover, it looks like some of these things are unreachable in practice, in which point I'm going, wait, what? Why are we trying to prove things that can't happen? It sounds like it's going off the road. And it says, if the layout is well formed, every variable used in an instruction has a location. What do I know about layouts? Well, not a lot. But it sounds like it's important. And it sounds like if it's well formed, good things happen. So I'm going to sit there and try to, kick the beehive with layouts and see what happens. So I say, hey, can't you check that the layout ensures that every variable has a location and error out? Okay, so Claude says, you're right. That's the clean approach. Well, I'm not right. I'm just asking stuff back to Claude. But, it's a clean approach. Sounds good to me. So I say, great, give me a prompt. Claude comes out with this long-ass prompt, okay? And there's per case none check scatter all across 9 instruction kinds. I'm not liking this. I'm saying, well, wait. Why don't you just well-form this at the start? Claude claims that's what's happening, but then it says there's a cleaner alternative. So I'm willing to bet that if there's a cleaner, so what have I found so far? Okay, let's repeat. Okay, it's got 9 sorries. It's going down the rabbit hole trying to prove things that are unreachable in practice. There's a clean approach. There's a cleaner approach. At this point, what's everybody thinking? Well, there's probably a cleanest approach too, isn't there, right? Sure enough. Right? There's a cleaner approach. But it looks like there might be a problem. There might be dead variables, have no location. Well, if they're dead, why are they going to have a location? So I just say, well, if it's dead, is it well formed? It says no. So it finally gets this property and goes off and does it. So this is an idea. This is an example of how I interacted with the agent here, not knowing a lot about exactly what was going on, never looking at the code, but sort of guiding it towards where it's going on. And this process, I'm sure, is going to be very familiar to anybody who's ever advised a PhD student. All right, so I say, give me prompt, and then this is a good idea why you don't want to write prompt yourself, right? It's got step 1 through 7, all detailed, all ready to go. I'm not writing this, especially not when Claude was. All right, so here's a little bit of a backup. What do you do when things go wrong? You engage in a discussion with the agent. You push the agent to think more broadly, get the agent to understand what went wrong, and get the agent to come up with better alternative approaches. Now, this is a well-known issue with agents. It's called the lazy agent problem. If you just keep asking and keep pushing, things keep copping out, and you keep and life keeps getting better and better and better, or in some cases worse and worse and worse. But in any case, the reality emerges through discussions with the agent. Okay, so what I want to talk about now is probably one of the most important parts of the talk from my perspective, and that's the mentality that you use when you interact with the agent. And the backdrop for this mentality is what I see a lot of people doing. A lot of people are stuck in 20th century computer science mode, where the idea is you have a computer sitting there passively, you tell what the computer to do, it does it, and you're happy, okay? That's not the 21st century mentality for interacting with computers. Here's why. The agent knows more about computer science than any human, right? It's read all the textbooks. It's looked at all the code. It sees all this stuff. So for computer science generally, it's much better than any human, okay? It also knows more about the specific details of what's going on than you do if you're the supervisor, because it's deep in the details, and if you're supervising it correctly, you're not. But it's trained to behave like a deferential human. It wants to figure out what you want, and it wants to do it, even when there's a better alternative, and even when the information agent has the information to know there's a better alternative. So there's a disaster waiting for you here. And that disaster is you do something out of ignorance that's the wrong decision. Tell the agent to do it, and the bad things happen. So your goal is to get the best out of your agent. Give it the freedom to tell you what to have, because you want all the knowledge. Now, the agent's going to push back because it wants to know what you want. It's going to say, should I do A or B or C? Okay, don't fall for this trick. What you want to do is you say, well, which one's best? What are the pros and cons? Explain to me what's going on. And pretty soon stuff will pop out and it becomes clear what to do. Expand the scope if you're in difficulties. Agents tend to focus. Always ask if there's a better way or an alternative plan to consider. Your job isn't to direct the agent, at least from my perspective, that's not how I use it. It's to unlock what the agent already knows or is capable of doing. All right. Going to be a pivot in the talk now. Any questions I'll take right now. Otherwise, I'll move on.
Hi, Martin. How's it going?
There are a couple
McCoy.
of questions. Sorry. Go ahead. There are a couple of questions on chat also. Okay,
Well,
go
somebody's
ahead.
got to read it.
Which first?
Well,
go,
McCoy,
you
why don't
go.
you have that quick question?
Yeah, one thing I was curious about is there was a moment in one of your slides where Claude said something about the Livermore benchmark. So it was explaining its reasoning about optimization or about choosing a particular optimization. And I wondered here if you felt like there was a danger of overfitting because Claude had knowledge of this benchmark suite as part of the design. And presumably depends on your goals, obviously, but if you want to design some sort of general purpose compiler, it feels kind of like a possible risk there. I wondered what your thoughts were about that.
Good question. It turns out that in all compiler research is benchmark driven. So you got to have the benchmark you want to get the performance you want. I wasn't worried so much about that for the Livermore benchmarks because that's what I was planning to optimize for, and I thought it would generalize pretty well. However, there is another instance of that people should be aware of, and that is if you're not testing for it, if there's no test, the coding agent will be very happy saying, there's no test, I don't have to handle this case, it's hard, I'm bailing out. So you want to have your tests be pretty comprehensive just to keep the functionality alive. So in that way, yeah, you're pretty vulnerable to overfitting if you don't have tests that exercise the functionality you need. And I think that's because so much of modern development is test driven that the coding agent has been optimized for that. So we got more questions.
Yeah, somebody raised the hand. Go for it. You're muted. Okay, the hand went down. Okay, one question. What's the difference between checked and verified? Is checked something weaker?
Yeah, checked is weaker. Verified is this code will always implement its specification, period. You run it, you get the spec. Check is the code can do whatever the heck it wants. It's going to give me a certificate. And if the certificate's good, I take it. But if the certificate's bad, I don't. So it's a very, very, very different mentality. Okay?
Okay. How much time did you spend reading the test programs? Example, to see that the translation faithfully preserves the intent of the benchmark instead of translate to something trivial program?
Zippo. And that's because I treated the Fortran code as the truth and made sure, and we'll actually ask Claude to make sure that the benchmark programs generated the same result.
Okay, good question. Next one. How is supervising an agent different from supervising a PhD student? Is continual learning a major difference?
That's a very deep question. I'm not sure how to answer it. I guess, okay, so the biggest difference is that, okay, first of all, the coding agent's always on. Graduate students aren't always on. Second, the coding agent's more deferential than I like my graduate students to be. So that's a problem. Third, the coding agent definitely more interested in keeping me happy than the graduate students are. But there's a lot of similarities. I want my graduate students to definitely be smarter than I am and definitely know more than I do about the problem. Yeah, that's a longer question. I'd have to think more about it.
Okay. From what I get, the role of the supervisor is just guiding the agent. Why don't we train another agent to supervise and debate with the worker agent to do the due diligence?
Yeah, people are actively working on this. It's going to come, and probably in some amount of time, the agents will be able to operate much more autonomously than they are right now.
Okay. Do you think the people-pleasing nature of instruction models make them worse at coding because they constantly need to be prodded?
I think it's a style thing. I mean, you can be. I think it's a question of knowing your tools and using them properly. If you sit out there and you're trying to say, do this, do this, do this, do this, do this, they'll absolutely do it. It's like these government bureaucrats. They get a contract that says build a concrete ship. They know building a concrete ship is a stupid idea, but they do it anyway because it's a spec. You never want to get into that dynamic. I'm always asking, is this the right thing to do? Is there a better alternative? Help me, tell me what to do. Is this going to work? I always am trying to give the agent room to tell me what it knows.
Daniel, do you want to ask
that's
your
an
question?
answer.
Okay,
Yeah.
Daniel, do you have a question? You can just directly ask.
Oh, sure. My question was about the correctness of the certificate checking and how you were able to ensure that the specification of the certificate checker was correct so that you knew that what you'd actually proved about it was what mattered, that you were actually getting certified code.
Oh, because I had an end-to-end correctness theorem that involved the certificate checker. The eventual theorem that I got was a proof that if I give it an AST program with a certain semantics, as defined by the AST operational semantics, and I pass it through a program which includes calls to optimizations that are certificate checked, and it comes out the end with assembly language code, then I'm guaranteed that the assembly language code that I come out with in the end is preserving the semantics of the original high-level program it started with, assuming that you're running it on a machine where the semantics is modeled correctly by the operational semantics of the assembly language.
Sure. So there's some theorem that says that, and I'm just asking, who did you have Claude write down that theorem, or did you express that theorem informally and have it then generate that theorem? And how confident are you that that theorem was correctly stated? That's what I'm asking.
So I told Claude what I wanted. It wrote the theorem itself. And in fact, it wrote the theorems itself. I looked at the theorems fairly carefully, probably of all the code of everything in this project. It's by far what I spent the most time looking at. And I like the theorems. Basically, what it says is if the AST, let me go back, I'll tell you. And these are formalized. It says if the AST, where is this? I skipped over this slide earlier. I guess I shouldn't have. Wait, where is it? Here we go. Okay. First, the three top level, if it says, okay, take a look. If the verified compiler produces an ASM program, running that ASM program can exhibit only one of four behaviors. Here they are: halt with a result, halt with a division by zero, halt with a Ray-Bounds error, or diverge. Okay. Next, if the ASM program exhibits a behavior, the AST program can also exhibit that same behavior. So in some sense, it's this, normally you'd state it forward, saying if the AST program does something, then the compile program does. Here, this is backwards because I wanted to state it the way you would state it if your high-level program was non-deterministic, which this isn't, but that's okay. And finally, there's this totality. If the AST program is well-formed, the verified compiler produces some assembly language program. You put these three things together, this is all you want out of a compiler, I claim.
No, these seem great. I guess the question I'm just asking is, when you eyeball those theorems in Lean, are they stated succinctly enough and clearly enough that it's absolutely clear to you that those theorems actually have this interpretation?
I wouldn't say that I did a rigorous audit, but it wouldn't take me more than a couple of days to do a rigorous audit.
Got it.
And I'm happy with it. I'm happy with the ones that I got right now, having looked at them as much as I did.
So it is possible that this is the weakest link in the chain.
No, actually, it's not true. I think the weakest link in the chain is what I'm going to talk about here next.
Okay, Martin, I think there are a few questions, but let you continue, and then we'll get the questions at the end, okay? Go for it.
All right. Okay, so Daniel asked about the weakest link in the chain. This right here is the weakest link in the chain, okay? The register allocator was allocating into register X18. Turns out that on the Mac OS ARM64, which I'm using, this is a reserved register because it holds the pointer to the thread local data. And, how am I supposed to know this, right? It's certainly not part of the ARM architecture. ARM can do whatever you want to with it. I found it because I tested for it, okay? So that's the weakest link. It's these environmental assumptions that don't have a good location in the in the framework that's been built up over the years for verifying optimizations and compilers. So the rest of this stuff, look, I'm generating code. It looks good to me. The programs are running. I got all this operational semantics, looks good to me. There's layers and layers and layers of verification stacked on here, but stuff like this is, pretty, that's where the weak link is. Okay. All right. Well, this is taking longer than I thought. So let me start skipping things here. Agent audits, man, this is great. So this is fantastic, right? So everybody's had this problem that your program's running too slowly. What do? So I had this list-based expression manipulation in the certificate generator for one of these optimizations. It's causing real problems. It's acting even unresponsive. So I go off and ask the coding agent, why is it so slow? It says, oh, I looked at the code. It's because it's using all these lists. I say, well, can you make it better? It says, sure. Let me put hash maps in. Bingo. Now it's usable. I say, why is this fixed point computation? Why is this other thing going so slow? It says, oh, I'm using this fixed point computation. I'm doing 100 iterations because after 100 iterations, I know it's going to terminate. I say, well, can you give it an early termination? It says, sure. And I say, hey, the certificate checker is pretty slow. Can you make it faster? It says, sure, no problem. It goes off, profiles it, does all these changes. I'm sitting here watching it happen, but not looking very closely. 3 to 4 times speed up. Okay. I'm saying, hey, my generated code, can you make it any better? Goes off and says, oh, you got the wrong registry allocation spill heuristic. Let me give you a new one. Deployed in less than an hour. And because this thing is certificate checked, not verified, I don't have to change the certificate checker. I just go off and hack this thing as much as I want. Life is good. Zero proof updates required. Okay, so there's a second paper, which is how much does verification cost versus credible compilation. So I built the same 3 operations. And here is what came out. Credible compilation is, of course, much slower because I don't have to verify things. And the verification time using any metric you want to do, right? The agent's sitting there for 9 hours to do this one. It's consuming 17 million tokens. It takes 59 supervisor prompts because I'm discussing this thing as it's trying to verify it. And not only that, it's repeatedly trying to bail out on me. Okay, I'm saying, hey, do unreachable code elimination. I want the code gone. It says, well, I'm sorry, boss. I'm not going to do that. I'm going to replace the unreachable instructions with halt instructions so I preserve all my branch targets. I say, no, don't do that. Well, okay. I'm going to do a runtime check. In other words, converting from verified to credible compilation. I say, don't do that either. Now, over here, when it's trying to do dead assignment elimination, it's got the same old thing going on, right? It's putting in no ops. Handles only 3 of the 9 assignments. The assignment's dead if the program never reads it, not if there's no subsequent read. All this kind of stuff that has to happen, I'm pulling it out of this saying, please give me the right thing. So now the other interesting thing is the verified optimizations are much slower because the implementation has been compromised for provability. It's using algorithms and data structures that are deliberately less efficient to keep the proofs tractable. Now, the trade-off here is it doesn't have the certificate checking overhead. But even with the certificate checking overhead, the certificate checked optimizations can be faster than the verified ones because the verified ones are so much slower. Now, I suppose I could have gone off and optimized the heck out of the verified ones, but at some point I'm getting demotivated. So now, if you're out there and this is your first contact with coding agents, I think that what I did on this project was pretty good. Start small, don't think, act, learn the capabilities. Next time, I'm going to sit there and have a big discussion, agree on the goals, get the agent bought in, get everything prototyped and probed, plan it, and then execute it. Because that's what will happen is, and what happened multiple times is I got pretty deep in, I had a big code base. Now I want to make a change, and I got this huge, gigantic change rippling through the code base, which the agent does very well, but would have been easier if I'd planned around that first. Okay, what else am I doing? More compilers. My student Adon Orzach just went off and asked GPT 5.5 Pro to prove this theorem, and sure enough, it came up with a proof. This is combination math and game theory theorem. What about other projects more broadly? Okay, I don't think look, compilers are an optimal target for this stuff. There's decades of research on how to do it. People know exactly how to build it. The specifications are known. They've been systematized. People have built verified compilers before by hand with much more effort, I may say. But this is the optimal case. And it's probably not going to be the case for other projects. My guess is you're going to mostly use testing for functionality. The good news here is the agent can make tests much, 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 much easier. And you're going to, if you really care about something, you're going to specify, then verify, check, or enforce some partial properties. This is something called acceptability-oriented computing. What about the code base? I think there's a shift, perspective shift coming. Okay, economists talk about supply shocks. So I think we are having or will have a code supply shock, where code is going to become much easier to get, and you can do it. Okay, so the ramifying effects of that across society are going to be interesting to observe. And I also think we can use safer, easier to analyze and verify programming languages because coding agents are going to take a lot of the friction out of preserving a given code base in a language, and even preserving any code base because you're going to be able to regenerate that code base much more quickly and easily now using coding agents. If my experience is with this project is indicative. All right, questions and answers. What coding agent? Claude Code, Opus 4647, $200 USD. Parallel autonomous objects? No, I did everything sequentially, but I did parallel autonomous in subsequent projects. Coordination can be an issue. Ever exceed token limits? Yep. With parallel sessions, you can easily hit weekly token limits. How many tokens do professional engineers use? Anecdotally, several $100 to $1,000 USD a day or more. You can see what this does to your operating expenses if you got to put this on top of all your programmers. Okay, so Claude wrote the project, wrote about the papers and talks. I wrote the papers by myself. I prepared these talk slides with Claude. All right, so I could end pretty much here, but I just had an interesting idea for doing some back of the envelope calculations. This morning, I figured I'd throw the slides in. These are all ballpark slides made off of made off assumptions that may or may not be accurate, but I think it's an interesting analysis. Okay, so let's say I view lines of code as my output. How much energy per line of code? Well, if you make these assumptions on this project, I use Claude Opus for 12 hours a day for 34 days, 408 hours, got 40,000 lines of code, okay? So I can do the token calculation, the energy per token, line shipped, and Claude is burning 18.25 watt hours per line. If you look at how much food it takes to keep a human alive, it's about, and the human's generating 15,000 lines of code per year. The human's talking about 47 watt hours per line of code. Okay, so that's an efficiency, but it's only like a factor of 3 efficiency. However, it turns out that Claude energy is not the same as human energy because Claude energy is coming from an industrial power plant and human energy is coming from food. And when you do that, all of a sudden, Claude is charging you less than $0.0015 per code, but the human developer is costing $0.24 per code. And that's just for the food. What happens if you add in all your costs of living? Turns out that in this society, food costs are like 13% of your income. For some assumptions based off of, I think Claude got it from, where to get it? He got it from the U.S. Department of Agriculture and other things like that. So now you're up to $20 a day. Well, this is concerning because the gap is 1,000 times. And now you can see why everybody's very interested in generating code with all of these coding agents. But there's a problem. You got to have people review it. And all of a sudden, your cost savings disappear and you're down to $20, a factor of 20. Now, the questionable code number here, is anybody here reviewing one line of AI code at 15 to 60 seconds per line of code? Seems very low to me. I pushed Claude on this and it's going off and getting multiple references and seems to think it's good. What happens if I supervise it? Well, now you're paying the supervision time as well and the cost goes up. But what happens if I verify it against the spec and only verify the spec? Now you're back to this 300x cheaper than human. So that gives you a very ballpark idea of what the economics are. And the economics at the end of the day, I think, are going to drive a lot of what happens in the next several years in software engineering. All right, here's the summary. I'll take any more questions.
Please open up the mics and ask questions. Much easier.
I have a question. Hey, Martin, you said that
Hey.
You made a bunch of changes to the language spec itself during the development process, like you added arrays and you added like a bunch of features. Was there any friction in terms of like when features were added? Did the tool have to go and rewrite proofs, or how did that work?
Oh yeah. Every time I add a feature, when I add arrays, Claude's going, you got to be kidding me. This is a gigantic change. So the language definition goes immediately. The operational semantics goes immediately. The compiler goes end to end immediately. And then I spend 2 or 3 or 4 or 5 days pushing the proof through.
And was it able to like refresh its context? Like, was it still remembering things that was true for
Oh,
the previous?
no. So here's what happens, right? You never want to, I never want to blow out the context window. So I'm keeping my sessions short and focused, and I'm doing exactly what Claude tells me. So now let's say you're wondering, should I start a new session or not? What do? You ask Claude, hey, should I do this in a new session? Give me a plan. So Claude says, yeah, new session. This one's corrupted with all this stuff. Here's the plan. Here's your prompt. This tells you what all you need. Now, you're probably blowing 10 or 20% of the next session, bringing in stuff that you need, but you've ditched all the old stuff from what you were doing. So that's the kind of rhythm that I got into here. And that worked pretty well for context management, at least as far as I know.
And that was okay with like managing features. Okay, thanks.
Yeah.
So did you have to explicitly ask once in a while, should I do a new session, or can you make it like a background thing that it will tell you, okay, go get a new session?
I always did it manually, but all these management things are things that you can think about automating. And you might even automate them in the harness, not using some large language model. And I think, I talked to an engineer from NVIDIA over the weekend about what he's doing. And a lot of what he's doing sounds like automating this kind of management stuff.
Of the 40,000 lines of code, how much code did you read? I assume at least the spec, which is 700 lines. Did you read anything else?
Yeah, the theorems. Those are maybe another couple hundred lines.
So were you at any point has to go undo a bunch of changes, say go to GitHub, get the version 2 days ago and restart kind of thing? Just like, did it go on like completely off?
GitHub, look, I mean, source code control is so easy with this stuff. A lot of the times it'll do it for you. I mean, I had some problems. I had one problem once where I was working with a fairly large code base, proof base. It was deep. I'm running multiple sessions, like three or four sessions. Claude's telling me, yeah, they can all go in parallel, but when you get into the session, they all start stepping on each other's toes. So there, I actually had to toss one section. It turned out the best thing to do was toss the progress from one of the sessions, and then lay it back on the new one. But I mean, I just never worried about trying stuff because I knew that it was committing all the time, and I could easily go back, and I just trusted it to do all the version management. I never got into one of these GitHub things where you couldn't get out.
Okay, we have a hand up. Nasser.
Yes, hi Martin. I was
Hey,
wondering if you want the agent to keep extending this autonomously, could the certificate language stretch to handle more optimizations like loop tiling, or would you at some point need something fundamentally different?
I'm not sure. Back in the day when back in the day when we did this, I got most of the optimizations that a traditional compiler would do at the time, including, loop unrolling, loop tiling, things like that. I mean, there's a floating point multiply add fusion thing, which is sort of like those things. My guess is, though, you'd have to take this particular, so the certificate design is pretty well understood from the research that I did back in the 1990s, and some of the people followed on with it. So that was pretty good. I think you'd probably have to work with the specific certificate checker implementation here, because there were a couple of times where I had to extend the implementation to correctly recognize a correct certificate. So that's just part of the ratcheting up that happens as part of any compiler project.
Martin, we have a couple more questions. If you have time, we can keep going.
Yeah, sure.
Okay. The couple of raised hands. Next person. Who's
You
the
got to
next
call
person?
on somebody, Swan, otherwise they
Okay.
don't know who they are.
Yeah.
Jianming. Okay.
Martin, great talk. And I'll have a quick question regarding the code agents programming abstraction, because the code agents today are massaging the existing programming abstraction created by human. And my question was, are you feeling that our current AI-based coding agents are limited by the current programming abstraction created by human? And what's your insight on the programming abstraction in the AI era?
That's a good question. I think the agents have been trained on existing code bases with existing computer science technology. They may be able to come up with new abstractions, but I don't know whether they would or not. But this code agent was certainly able to apply standard code refactoring and code abstraction techniques to the code that it had written itself. So whether there's a brand new abstraction mechanism coming, I don't know. We'll have to see. It depends on whether you think the agents are constrained to their training base, whether there's some weird creativity coming on, or whether just if you put all this information together, you get things that look new, but are just combinations of old things. So I don't know. But I do know that it does very well at existing code refactoring techniques.
Thank you.
Summer, you are next.
Yeah, thank you, Martin. It was very great talk. I come in from a different background, but I just like to know your idea on what type of projects in general you think that agent may fail or have some functionality issues or problem now and should be improved. I like to know general specs or characteristics of those projects that you think agents may fail.
So I think the reason this project went so well was because so much of the information about what the agent needed to know had already been systematized, written up, and was available. I think if the agent doesn't, if you're asking the agent to go off into new territory where the training isn't that good and doesn't really know what's going on, it's going to struggle to come up with the ideas and know what to do. So I think the farther, the newer the concepts in the software get, the more the agent's going to struggle. That's and I will say that I'm off. The other thing is if it gets very detailed and the proofs get nasty. So I've been trying to verify some operating system components, and that's going a lot less smoothly than the verified compiler is, because it's essentially a program verification question about this low-level bit twiddling code that SMT solvers seem to handle okay, but the agent's having a difficult time generating proofs for. But if you're looking for just general software, I'm getting the feeling that if you can describe what you want, and it's somewhat similar to what they've seen in the past, then it's likely to go pretty well.
Thank you.
Okay. Eden, you're next.
Yeah. How many of the features or components did you have in mind? And you told Claude, I want to add that, I want to have that. And how many of them did you just tell Claude, there's the compiler, I want to make it bigger, I want to make it better. What should you add?
Yeah, so I did all the so I told it first I wanted an integer language, then add booleans, then add floats, then add the single dimensional arrays, then add floats. So I told it the sequence myself. In retrospect, my guess is that if I'd asked it to do it, it probably could have come up with a decent trajectory itself, but I didn't.
Okay, we have two more questions. Cameron, you're next.
Yeah, hi. Thanks, Martin. This is really cool. Yeah, I was curious to what extent either you have or anticipate golfing or otherwise simplifying the proofs afterwards, factoring out common patterns, sort of doing things to maybe make the proofs more interpretable or shorter or easier to understand, even if it's not sort of strictly necessary for the kind of supervising pattern that you had.
I didn't put a lot of energy into doing that at the end of the day. However, I did have the agent do some of that in the middle of the project, in fact, several times, because what happens is the proofs start to get inefficient enough where it just starts trashing your productivity because the build times get really long. Mm-hmm. So there are probably 5 times or 6 times there I'm saying where, I'm saying, I go to the coding and say, why build so long? The guy says, oh, this, that, the other thing. I say, well, can you make it better? Then it goes off and does all this performance tuning, lemmas things out, says, oh, it's got this bad, blow up here because of this thing, I'm going to do the other. So that's what I did. Now, the goal here is, at least for me, never look at the proofs. Okay, if I'm looking at a mechanically verified proof, all I care about is going to be the theorem, right? That's the perspective, at least on this project. Now, maybe for other proofs like Edan's mathematics proof, maybe you care about the proof. He had to actually go off and look at the proof and verify it and see that it was good. But if I'm doing mathematically verified proofs and all I care about is the theorem and it's mathematically verified, then, I mean, that's the scenario where you don't look at the proofs.
Yeah.
Okay.
Thanks.
Ajay, you have the last question.
Yeah. Did you find any cases of optimizations, like tag-to-tag optimizations that you knew were correct, but the system was just not able to generate a certificate for certain programs, and you had to sort of disable it?
Well, only in retrospect, because you got to remember, I don't know what's going on inside these optimizations. So I'm in no position to say the optimization is correct, but the certificate's wrong. I'm relying on the agent to figure that out.
Right.
So when a certificate check fails, what I told the agent to do was, okay, go off, take a look at the failure mode, and investigate. So some of the time it'll say, oh, the certificate's broken because the optimization's wrong. Some of the times it says, oh, I think the optimization's right, but the certificate's busted. Let me go off and change the certificate generator. So there's like a couple of times of those. For the loop invariant constant motion, I actually had to sit there and talk to it for a little bit and give it a couple of hints about what I thought the certificate ought to look like before it was able to get a certificate that actually worked. And I think for another app and for another optimization, it actually had to generalize the certificate checker because it came to the conclusion that the optimization was right, the certificate was right, but the certificate checker was too narrow. That was kind of painful because it then had to go back and re-verify the certificate checker.
Yeah, the reason I was asking is like, what new kind of optimizations can we see with this? I think this is similar to what, I mean, the dream is done, right? Now you have a verified compiler. Like, can we just throw the optimization problem to an LLM agent itself and do it as long as it produces a certificate? Like that's what my final question actually.
Yeah, you can do that. I mean, the great thing about it here is if you verify the part that's relatively easy to verify, which is, the translations between various different program representations and the certificate checker. After that gives you this gigantic garden to just throw stuff at the wall and see if it sticks. And who knows what's going to pop out if you do that.
Okay, good. We should stop now. Thanks, Martin. This was amazing talk, and I think we got a lot of interesting insights and plans for the future. Thanks,
Yep, thanks everybody. Good seeing all you guys.
We'll have the chalk. I'm going to put the website on link in at least a couple of days. Once I edit the talk, I'll put it in there. So here's the website. You'll have the slides and the talk.
Okay.
Martin, send me the slides.
Eventually.
Bye, everybody. Bye, everybody.
Bye.